Hello, hello. This is going to be a little weird. I'm testing the audio. I have a 3D print going, so I'm using a different mic. I want to make sure you can still hear me. Right, a little bit of lag. One sec. Oh goodness. I think it's good. Can you hear the 3D printer? It's a really annoying high-pitched whine. If you can't hear it, I've done my job well. Yeah, so I've got a lav mic. Based on what I can hear, it sounds like everything is perfect. I'll turn it up a little bit. Yes. Yes, it's quite good. All right, sweet. Alright, I'm turning it off. I can't deal with the lag, man. I can't deal with the lag. But we're here. We're ready to go. Hi, Mr. Aviation. Welcome, welcome. Again, trying something weird with the microphone. Let me know if it sounds terrible. I've got the old one on standby. Using a lav mic literally taped to my face because I had to call an audible when a 4-hour print turns into a 9-hour print. things happen. Anyways, we've got an awesome topic today. I'm so excited for today's stream because it's redemption time. It is redemption time. We've got our new buck converter design and we're going to test it. We're going to be doing line, load, ripple testing. It's going to be sweet. This is the little board that that we made. You might notice that it looks a little bit different. There's a couple like little, what are those? Little bodge capacitors on there. Didn't have quite enough output capacitance, and by that I mean enough MLCC output capacitance. There's plenty here, but the ESR of these electrolytic caps was too much. It was too much. I had to add more MLCCs because at 1 megahertz, man, the parasitic inductance and resistance of this guy was just very unhelpful. Well, that's good. Yeah, so I've got an EQ here, and I turned the high frequency all the way down. So good. I'm glad that hopefully it's not annoying. If it is, I can tweak it and see what I can do about it. By the way, welcome NoCorp. So yeah, I'll take this out a little bit. What we're printing is, it's time for, just so you know why there's the annoying sound in the background. So tweaked this because my only complaint with the old storage rack for these parts is that there's not really anything to grab onto to pull it out of the rack. So I tweaked the model a little bit, added this, tweaked this to make it a little more rigid. You got a free 50 volt 10 mic cap today. Only one? You got one free 50 volt 10 microfarad cap? That's... Huh. How did you get one free 50 volt 10 microfarad cap? Anyways, so I was printing this and it's a little too loose. I tried to tweak the model to make it print faster and I hosed up the whole geometry. Anyways, so started playing with some other ideas to make it print faster. Turns out blocks print pretty fast. got one that has a lot of, I mean, it's hard for you to, better than none, that's true, that's true. So just kind of played around with it. This one's got a little bit of rigidity, this one's got quite a lot of holding force. It's an excellent friction fit. So printing a couple new trays, and that's what the noise is all about. I think that's enough messing around. I said I have a surprise for you. When I zoomed out, you could probably see it, but I couldn't resist. I couldn't resist the cheap goodness of these. Maybe I'm just sick of playing around with all the resistors. So we won't be using the resistors today because we have the right tool for the job. We got a little electronic load. It was a couple bucks. Based on a preliminary test, it has not yet failed short, so hopefully I got one of the good ones. The accuracy seems within, you know, 1% or 2. Yeah. Just getting things framed up here. Yes, yes. So, pretty excited, right? So it's the old design. We couldn't quite get the output current that we wanted. Couldn't have as wide of an input voltage range as I would have liked. There's just a lot of things about it that were kind of not great. And then when sorry, apparently I'm 12. Anyways, so you know, just a lot of things about it that weren't great. And so I really think that this redesign, you know, this new buck converter design using a regulator and a rectifier diode, I really think it's going to be a move in the right direction. So I hope you guys are excited about it too. But since we got the proto board, we've got a 5-volt one, a 15-volt, and a 12-volt one built. We can go through, test all 3 supplies out of circuit, and then we're going to solder it into the circuit using the test point pads on the bigger proto board, and then we're going to circle back and test out the flyback. We're going to finish testing the stinking flyback, which we couldn't do because our 5 and 15-volt rails kept exploding. Yeah. Pretty exciting stuff. Pretty exciting stuff. Hope you guys are having an awesome day so far. I know I am. Yeah, we'll get the scope fired up. Let's make sure that's working. Let's make sure that's working. Picture in picture looks a little small to me. I don't know what you guys think. Let's tweak that. Sweet. It looks like we are all ready to go. Okay. We'll finish getting this wired in. Let's see if I can find a way to get the module in frame for you as well. Oh, look at that. You can see the whole thing. Nothing to miss. So what I'm going to be looking at here is the input voltage ripple. Oh. There's one more thing I want to do before we get going. Burnt myself with a soldering iron 5 times. Yikes. Sorry to hear that. That's not fun. I've got a couple scars from that. This one is my favorite scar from a soldering iron. I don't know if you can see that. This was from when I was much younger. I was very excited about a project, so I was working on it way too late at night, and I actually fell asleep while soldering, and like I just fell asleep and like, yep, literally touched myself with the iron because I passed out while soldering. Fun times. Better than throat mic. Better than throat mic. Yeah, electronic load. Oh, I see. No corp. I think you're catching up. Like you hopped in and you're catching up from the first couple seconds. No problem at all. Yeah, on the output cap. On my big MLCC, the ESR/ESL was too high. And yeah, I'm super excited to play with this. Actually, that reminds me, I gotta plug in the electronic load. Cool. Yes. So, let's see. I remember this had a nice big. Can you see that all right? Do I need to tip that? I think you can see that okay. I mean, I'll read it off for you anyways. But that's volts and amps, top and bottom. I know it's a little different than the two that you'd showed me, but these were the ones that were available on Amazon, which meant I could get it in 2 days, which was pretty cool. Alright, cool. Yeah, the rest of it's a lot less important. It's just watts, amp hours, watt hours, and equivalent resistance, which, if you know volts and amps, you know, the rest of it's kind of irrelevant. Okay, so we got input voltage, so we can see input voltage ripple, and now we've got V out, so we can see output voltage ripple, channel 1 and channel 2 respectively. I'm going to get those both set up for 1 amp per, or sorry, 1 volt per division. Yeah, channel 1, AC, 1 volt per division. We'll bump that one up a little bit. Channel 2, 1 volt per division. Yeah, I'll be ambitious. Let's go 100 millivolts per. AC. Excellent. Oh, that is super noisy. Got both probes set to 10x. Should be ready to rock and roll. Rewinding transformers. Rewound a microwave transformer. Oh. Yeah, I think I've seen that before, where you take like a gauge 0 wire and go around with it, just to see how accurate our electronic load is. I think I'll put one of my meters in. Oh goodness. Oh, I'm wired in. Can I reach the wire rack? Yes, I believe. Sweet. So we are coming around. Okay. Alright, so now we're wired in series with the electronic load. Got the ammeter. So we got volts out, amps out, which I guess is kind of redundant, but I trust my meters a lot more than I trust this cheap Chinese supply. We've got input voltage coming in from... Ooh, sorry. Tape came undone. Oh goodness, this probably sounds lovely. Mr. Aviation, soft start vid. Cool. Yeah, soft start. That was a pretty cool... Well, I forget the full title, but it was like how to not blow stuff up. Absolutely. Soft start is super important. Alright, I'm done. I'm done touching the mic. I got it reaffixed to my face. We are good to go. Yeah, that was a good video. Like, I thought it was really good because it was just starting to touch the nuance of... Alright, I'll get back to this thought. Hopefully. But we gotta start testing, man. Volts and amps both set to 0 on the load. Here we go. 4.967 volts out. And one of the things that I noticed is that the input capacitance wasn't quite sufficient before. So when I was probing on this side of the ferrite bead, I noticed just ridiculous voltage ripple. let's see what happens. Let's see if I totally fixed it. Start pulling some current out of this thing. Got 0.9. 2 amps out. Woo! Yeah, maybe not quite enough input capacitance. Oh, no, we're still doing good. We're still at 4.9. Oh, yeah, we're good. Okay. That was a good spot check. Excellent. Alright. So, I was going to start with line regulation. And to do that, I'm going to set... half the output power seems good. Let's set this thing to 2.5 amps. Let's get our fine adjustment tweaked. 2.5. Whoop, boy. Looks like 1 volt per division was a wow, really? No. Are we really getting 1 volt of output ripple? That is obnoxious. That's actually terrible. Alright, let me just make sure that that's not the ferrite bead. Oh, now. This is more what I would expect. Oh, we must be hitting a thermal. Maybe our ground clip isn't on there very well. Our ground? What is this? Can I help you? Scope. Could you be less insane, please? Alright, let's... I think it's because I've got a banana clip going onto a literal solder joint. I think that's not great because we need to break through the flux residue. So now I'm pretty confident I've got a good contact. That might be a thermal. Let's turn down the input voltage. Soft start makes ankle grinders less scary. Yeah. I'm actually... Do you know what micro the load has? The one I have is 8051 based. View the board. Might be occluded depending on where you move the board. Oh! Sorry about that. Sorry about that. Back in view. My bad. I'm not sure. I don't know where the micro is on this guy. The screen is blocking a lot of it. Can't really see it on the top. Unless it's this tiny little unmarked IC over here. Which would be... Or if it's under the display. I think it might be either under the display or this tiny unmarked chip. It's not something great. Based on the fact that I can hear the pulse width modulation on this thing, I'm gonna say it's pretty slow. Alright, so what I want to do is I want to bypass that ferrite bead again and see if that input ripple drops, because this is gonna have a common mode rejection, or sorry, a PSRR, a power. I don't even know if that's a term typically used for switchers, but whatever. I'm going to use it. But basically how much noise it can reject on the input. And if, for example, we have a lot of noise on the input because of a series ferrite bead, that might be coupling directly into the output. Alright. What is our frequency? we should be looking for about a megahertz. That's what I would expect to see. We are not getting a megahertz, which either means that we're in the light load operation or the thermal protection routine. I noticed that my copper planes are pretty small on here. So soft start is pretty interesting because, whoa, come on now. Got 1 amp out, 0.9. That is interesting. This is very interesting. The soft start routine for an inductive load on an inverter is pretty interesting, because if you keep ramping up your sine wave in the same direction, if you keep trying to do your positive half cycle, you can actually continue building energy in that inductor or that motor and eventually have what's essentially a short circuit. And there's a lot of fans and crap in here today. Hopefully you can still hear me. But if you kind of like overcurrent trip, and then you try the negative overcurrent trip, then you try the positive overcurrent trip, then you try the negative overcurrent trip, eventually you'll build up the momentum of the motor, of the inductive load, and then it will start. So you can handle starting big inductive loads if you've got the right kind of soft start routine on your inverter. And I certainly intend to implement that. So that should be a really cool part on the scope. Right now we're seeing 2.32 kilohertz, which is weird because if you've got the new version of the schematic, which is in the description, should be text searchable. Actually, I don't even have it here. This is the old version. But if you have that, what you'll notice is that it's programmed for like a megahertz. We've got a 20K programming resistor. Alright, we're going to leave the ferrite bead in series because it is not affecting us significantly. Should be great. Which controller? Yep, that's the one. The LMR 14050. That is the controller that we're using. I had to bodge a couple extra output caps down here to get enough high frequency output capacitance. Bodged an extra input capacitor up here because I didn't account for enough DC bias effects. 24 volts is kind of a bugger when you've got an MLCC at like 70% of its input voltage range. It's like 20%, 10% of its nominal value. It's it hurts. But yeah. Anyways, we're just gonna measure the ripple and it's gonna be alright. Alright. So cursor A, cursor B. Looks like we're getting 760 millivolts of ripple. Can anyone say needs more output capacitance? Because holy crap, we need more output capacitance. Thankfully, I've got a new rev of the schematic where I'm piling 10 microfarad caps and a bunch of lower ESR electrolytics to get that down. Anyways, we are at 2.5. We're at 2.5 amps. 2.5 amps. We're measuring 0.76 volts of ripple, and we are at an input. We're going to do this sweep from 16 volts up to 30. So at 16 volts, we're at 5.0 volts. I'm going to crank the input voltage up to 30, which is the high end of our sweep. We are now at 30 volts in, and we are at 5.0 9 volts out. That is excellent. Excellent rejection, but a ripple. Oh boy, that ripple. I'll check the comments in just a second, guys. I'm sure you're making comments. Hey, it actually went into like the proper mode and wasn't obnoxious for output voltage ripple. Hey, look at that. It's actually reasonable with yeah, still around 700. I don't know what that intermediate mode we were stuck in is. Whoa. But I have a feeling it has to do with thermals. Yep, that is smoking hot. Yeah. Yeah. Oh my goodness, yeah. Unfortunately, I don't have anything more than a 4.7 mic 35 volt cap on hand, so I'd have to put like 18 of them here in parallel, and it would just turn into this massive blob of capacitors. So, I'll fix that later. I'll just be happy that we're in regulation for now. Yeah. So let's see. We got 0.09 volts delta, and our input voltage changed by math is hard. I'll just punch it in the calculator explicitly. Wow, that's excellent. So that's 0.64% line regulation. That is much better than the old design. I don't remember exactly what that number was. Desolder near. I've got a bunch of them. Like, I've got the caps. I just don't want to waste them all. I don't know. That's the soldering iron. Don't mind that. It's going into like a standby sleep mode. I should really turn off that beep because it drives me nuts. Alright. So I want to do load regulation next. And we're going to do a 0 to 4.5 amp sweep. So at 0 amps, we're going to run all these at 24 volts in. Alright, there we go. 24 volts in. And 0 amps, we are at 4.977 volts. Let's crank her up, shall we? There's 4.8. 4.9. Oh, wait, right, we wanted 4.5. Now this is going to be, I've got to be kind of careful to not do this for too long, because there's not enough thermal mass on these tiny boards to actually handle it. 4.5, and now we're at what? 4.928 volts. So that is also excellent. So we changed by... Holy cow. That is absolutely excellent. We changed by... Is that 49 millivolts? I think I'm reading that right. Might be off by power 10. So our load regulation is basically 1.1%. That's pretty good. It's good enough for me. Alright, I was implying a donor board. I'm terrible and have old prototypes, computer motherboards, just in case I need stuff. That's... Oh! I might have some boards I can sacrifice to the cause. You know what? One moment. I'm going to see... Alright, I gotta see what I can find. I think I've got some big caps around here. Old projects, man. Old projects. They're great for spare parts. Alright, I got the box of parts from the old UPS and plant light project. What? I'm not a pack rat. Pretty sure. Pretty sure I've got some parts in there. What temp it is currently? Great question. I'm not positive, but I know how to find out. I'm grabbing an adapter. So this multimeter can do thermal as well. Excellent. You guys ask excellent questions. I can tell you it was over 150C. I know that for a fact. Let me get this thing loaded and we'll check out the temp. I'm feeling Celsius. You guys alright with that? Oh wait, what? Didn't need the adapter. That's only if we're using like a type K. They gave a designated. Alright, let's make sure we've got it in the right way. If I put my hand on it, should go up. Come on now. Oh, don't tell me it's broken. There we go. There we go. Yes, definitely. So we'll turn on the load. We're at 5 amps. Put this on the ground plane. Hear that part. Whoop. I know it'll hit TJ Maxx. So the ground plane's at 70C. Yikes. Ground plane's probably 90C right now. Basically 100C. Yeah, it's hot. It's too hot. Yep. So way too hot is approximately how hot it is. While we're using our meter to do weird stuff, yes, I don't remember whether, I think capacitance, I don't remember if I measure from here to here. I think it's here to here. I'll have to grab my leads. These might be like 22 mic MLCCs, which would be awesome. That's ohms. That's not doing anything for us. One microfarad? Really? Trash. So it's 1 microfarad and just like 300 volts. Well, that's a shame. I've got some of these though. I've got a couple 10 mic 35 volt, which is better than nothing. I'll put 3 of these on there. What we're using in the next version is 10 mic 50 volt. Well, I'm out of those, so hopefully we don't need more than 3. But yeah, let's tack them on the board. The 5 volt one needs more output capacitance than the other two, so if I had to pick one of these to put these caps on, it'd be this one. And camera. Pour alcohol on it. Put it outside. It is a little cooler outside. Right now, I cool it with my finger. I mean, in the final design, this ground plane is going to be massive, right? This is getting soldered with basically a computer mother. We've got like a 12 by 12 sheet of copper that this is going to be tied to. With thermal vias and all that, like, this is going to be fine. It's dissipating a couple watts. That's not a big deal. But when your board's, you know, the size of a grain of rice, it's easier to hose up. Alright, getting the 10 mic cap added in. Just gotta melt the plane a little bit. Oh, look at that. No problem. Based on, I think these will be about 70% derated as well. So 10 mic, 70%. These should give us about 3 microfarads output capacitance. Oh, wait. No, these are only biased to 5 volts. They should be pretty good. They should be giving us, like, probably 70% their rated value. That should be no trouble at all. Don't mind me, just piling some capacitors. Literally piling them on the board. Never mind that. Can anyone say quick and dirty prototype? True fact. Designed this board kind of half-baked. That's why there's a mountain of capacitors on it. But basically just got the framework in place. And knew we could figure out the rest later. Wanted to make sure we could get it in time for the stream. Mr. Aviation, did you hear that? Not sure. Oh, the 739 Max. Is that the 739 Max Q? Like the plane that was... Yeah, that's a shame. That's a shame. Alright. Let's see how these are looking. So there is one probe, voltage. No? Did I miss? Did I miss again? What? These crazy little things. They mostly work. Once you get your probe in there, you're good. Alright. Sweet. Oh, look at that voltage ripple. That looks way better. It's amazing what happens when you have enough output capacitance. Let's load it down, see what happens. Hey! That looks much better. That's great. And actually, did that bring our switching frequency? Man, that was a super insufficient amount of output capacitance. It was wrong enough that it screwed up the switching frequency. Right then, and probably why it did that is because it was messing with the feed forward. So the feed forward cap was probably going absolutely nuts because on the feedback pin, because our output voltage ripple was way more than designed. So that might actually improve our line and load regulation considerably. Input voltage ripple looks fine. Output voltage ripple is now... we gotta switch this to channel 2. Output voltage ripple is only 148 millivolts, which, all things considered, is a lot better than a volt. We're on a 5 volt rail. That's still quite a lot. We're sitting at 3 amp load, but still. So we're sitting here And you know, that's kind of like compounding negative effects. Might need our scope again? Oh, hopefully you can see the scope. Because if the switching frequency gets reduced, the current ripple in the output inductor is going to increase, which is going to increase your output voltage ripple. So it's, hopefully I said that right, hopefully I didn't mix up the words. So it's like, if the frequency gets reduced, that'll increase the peak current, which will mean that we need even more capacitance to make it's, yeah. So it's good that we're switching at a megahertz, where we should be. Woo! That is pretty toasty. Anyways, 5 volts out, and we've got 0.15. So we're at 3% ripple right now. Not great. Not terrible. I'll allow it. Anyways, we should be able to bump this up to, yeah, we're at 6 amps right now. I wouldn't want to stay there a long while, but we got up to 6 amps out. So, yes, I'd say that electrically we've got plenty of margin. Thermally, we have enough margin. Trigger menu. Channel 2, because, oh my, there is not a lot of input ripple. There we go. Excellent. So I just want to make sure that we're not changing line or load regulation much. We were at 4.977. That's almost exactly the same. Go up to 4.5 amps. We're now at 4.939. Hey, we got better. We're better. We were at 2.8 before. We're at 3.9 now. That is awesome. So recalculating, we're probably at like 0.5%. We're probably 0.5% for both line and load regulation. The math. So when I said that I designed this in a hurry, that was a bit of an understatement. I probably spent a sheer total of 20 minutes designing these power supplies, and there's 3 of them. So the level of rigor applied was very, very low. Designing 3 power supplies in 20 minutes is how you miss the mark on your output capacitance. Do things in a hurry. You'll find you make a lot of mistakes real fast. That's what it was. That's what it was. Anyways, so efficiency. We want to do 1 amp, 3 amp, and 5 amp. All right. Yeah, I wouldn't say the math is off target. It's just I made some assumptions in the math that turned out to be false, and that's how we got here. So we're at 4.96 volts, and watts. Yep, because we're at an amp out. Divide that by 24.2 times 0.24. That's what we have coming in. We're at 85% efficiency at 1 amp. That's not bad. Let's crank her up to 3 amps. 3 amps, we are at 4.95 times 3. 15 watts out. Should have been able to do that in my head, eh? And 24.2 times 0.72. Still 85% efficient. Not too bad. Alright, 5 amps out. So we'll be at 4.9. By the way, the nominal output voltage of this supply is actually 4.95 volts. So we are doing quite good here. Times 5, so we should be, oop, that's 6. Oh boy. Yep, 5 amps, and we are at, divide by 1.23 times 24.2. Turn it down before the thing blows up. We're at 83% efficiency. Wow, that is pretty good. I expected our losses to change more considerably with load level, but we were pretty much 85% the whole way. And this is going to be our worst supply for efficiency because it's got the biggest voltage transformation ratio. Sweet. Alright. Power it down. What do you guys want? 12 volts next? We should be able to burn through this pretty quick. 12 and 15. I'll start going for 12 unless there's a riot in the comments. V in. V out. Yep. Sweet stuff. I love it. I love it when things work. It's so much better than the NCP 3020 where it was just like, oh, right here? No, we're good. The thermal mass is really small, so it cools down fast. But it also heats up fast. So we've only got this little plane on the back. You can see we've got the little thermal relief, some thermal vias there. Like, we didn't totally neglect this chip, but when your whole plane's only maybe 2 square inches of copper, it's not a whole lot when you're putting, right, we had 5 amps, so we had 25 watts coming out, times 1 minus 0.83, so we were burning about 4 watts on this board. That's a lot of heat for 2 square inches of copper. So no, I'm good. Maybe I flinched a little. I've just gotten into the habit of kind of touching things briefly when I expect them to be hot, just in case they are. That's a very good habit to get into. Right, got the positive, the ground clip for the scope. Yeah. Hopefully I didn't sound too defensive, JD. When you asked why the math was so far off, I'll admit, I was a little triggered. I was like, the math was off, for sure. Hopefully you don't mind. I don't like that the math was off. I don't like that I designed it in a hurry. But at the end of the day, the level of rigor was adequate for what we're doing here. This was basically, I saw that the dev kit from the vendor was like $35-50 for one dev board from TI. I got 20 prototype PCBs and enough parts to build 5 of these for the same price as 3 of those dev kits. So I was like, kind of hard to justify buying the off-the-shelf kit when you can literally do it cheaper. Anyways, we got 24 volts. We're all wired in. Punch it. Oh wait, nope, not quite. I gotta take off my jumper across this ferrite bead, and I'll do that on both of these supplies. Nah, don't mind. All right, sweet. Yeah. So I was thinking maybe we would give these away as like a little something fun. I don't know if you guys want boards with a bunch of bodged capacitors on them in a literal pile. Maybe you do. Maybe you do. I mean, they still work. So I know I put 28 volts on this board, but I think the controller can handle up to like 40. So as long as you don't need a lot of output power, you could get pretty good performance here. Okay. 12 volts out. Picture-in-picture mode. Let's move on to our next supply. Okay, we're doing line and load regulation. Line regulation, we're going to set this to 2.5 amps out, just like the other one. Uh-oh. Yep. Looks like our input capacitance or our output capacitance is not quite enough. That's annoying. That is very annoying. I tested all of these to 5 amps just to make sure the design worked before the stream. Alright, let's try it now. No? Yeah, there we go. Alright, so yeah, it's the input capacitance. That's a telltale sign of insufficient input capacitance. Well, I mean, and the voltage ripple, that's like volts. Let's see. In this case, let's see if I can get by with a couple more of those. I'm digging through my other box of parts, trying to see if I can find some MLCCs. Not seeing any. Got thermal pads, got all kinds of stuff. .2 mic, 10%. Oh, no. I'll just pile on a couple more of those 4.7 mic, or actually, you know what? Let's just bypass the ferrite bead for right now. Anyways, so we got the 12 volts out. We've got a crazy big output voltage ripple. We've got cursors. Cursor A, cursor B. We've got about 600 millivolts. Ripple. Not so bad. And we'll pull this down to 16 volts. 16 volts. We're looking at 12.04 volts out. And pull it up to 30. We are at 11.5. Pull it back to 24. .24 volts. Are you guys familiar with the equation for line and load regulation? Yeah. Yeah, thanks, No Corp. I wouldn't say it's that hard to model. Yeah. Yeah, if you want me to dive more into line and load regulation, I'm just kind of blasting through the math and the measurements here. If you want me to slow down and kind of explain what we're doing, just let me know. Yeah. Yeah, I mean, considering that it doesn't blast itself off the board, 20 minutes is not enough time to design a supply. This is something where if you're really doing a detailed analysis of a power supply, you can take days or weeks. Like, you can spend a lot of time analyzing a supply to really make sure that it's perfect. But in this case, balancing... Yeah, I know, the NCP 3020. That really irks me. It really irks me that doesn't work. Because the datasheet's rated for... Yeah, it's rated to operate up to 28 volts, but the internal gate driver kind of self-destructs if you operate it above 18. I don't think that makes the part rated for 28 volts. I think that makes the part rated for 18 volts. But it was... If I would have read the datasheet more carefully, I might have caught that, but it was a pretty subtle nuance. They bury it pretty hard. You can see this thing switching between different operating modes because of all that excessive ripple. Yeah, with enough input and output capacitance, we'd be in that mode. So we went from 11.5 up to 12 volts. So we've got half a volt change on the output for a 30 volt, or sorry, for a 30 minus 16. 3%. That's not great. But considering that we're tripping like a fault mode on this thing, it's not bad. And actually, 3%'s probably still good enough. It's not great, but it's probably good enough. Let's do the load regulation. 0 to 4.5. Let's make it scream. So we're at 12.08 volts. Let's get this thing fired up. Whoa! One flick of the wrist and we're up at 5.5. Okay. So what was I doing? Right, looking at the output voltage. 11.8 volts. So we're at basically 12.1 minus 11.8, so it's basically 0.2 volts divided by 4.5. We're at 4% load regulation. It's not too bad. Again, once we get this thing dialed in with the right input and output caps, that'll be better. It'll be closer to that 0.6, 1, that kind of 0.5%, 1% range. But we'll get there. Let's take a look at the efficiency. So we're at 24 volts in. We're going to set this to 1 amp out. Alright, so we got 12 watts out divided by 24 times 0.55. 91%. Will you give me that? 90.9 repeating, basically. I'm going to call that 91%. Okay, let's crank it up to 2 amps. Not quite there. 2 amps. So we're at 24 watts out. Oh my goodness. Yep, still 90% efficient. Excellent. Oh, wait a minute, that was 2 amps. That's not right. 3 amps is what we were going for. Please? Yep. So now we're at the... I'm going to actually calculate this one because we're starting to lose voltage. Times 3 amps. We got 35 watts out. What was the smile for, No Corp? Was it just the oscilloscope going absolutely berserk because of the excessive ripple happening? That couldn't be why you're laughing. Oh, it couldn't be that at all. I'm sure it's something totally unrelated. Yep, we're at 91% efficiency at 3 amps. Oh, pull it up to 4.5. Whoa, we hit the thermal limit. Alright, I'm going to let this cool down for a sec. Yeah, it's pretty toasty. Yeah, it's greater than 90. It's greater than 90. Yep. This one was 91 proper. 91. Boom. I mean, considering that this is not synchronously rectified, this is a diode rectified buck converter. And this is not a light load either. This is a pretty substantial load. And to be able to take this kind of abuse, and this is a pretty good part. This is a pretty nice supply. Considering the fact that it's dealing with my half calculated input and output capacitance and all this nonsense and a wide input voltage range, and it's a pretty nice part. Gotta hand it to TI. Like, yeah, I kind of went down a class apart, but went to what I see as a better vendor, and turned out alright. Okay. I think we're going to be at about 11.8 volts. I'm going to calculate this beforehand so that we have a chance of getting the output power before it hits the thermal limit. Turns out operating at the much slower frequency is causing much higher losses. I accidentally shot it up to 6 amps. My bad. Oh, no problem, JD. You gotta head out? Is that why you're saying that, or are you just saying thanks in general? Dude, I'm loving it. I'm loving every second of this. Times 2.71. I saw it before it screwed up. So 2.71. Yeah, that chip is hot. That chip is really hot. And the ground plane is also very hot. The whole board is quite warm. The whole board is quite warm. Oh my. We're still at about 91% efficient. Yeah, but the thing is, 91% efficient means that we're dissipating, what is this, 12 times 5? Oh, still about 5 watts on the board, 5.4 watts. It's not too bad. Still quite a lot for a board of this size, but I'll allow it. So I'm not sure if we're going to need to bypass the ferrite bead on the next board. Not sure. Might be okay. Okay, input voltage ripple. My goodness, I keep getting that clip. And output voltage ripple. Let's see how we do. Cool. No problem, JD. No problem. I am absolutely happy to share this with you. I have a lot of fun. I have a lot of fun doing these streams for and with you guys. I really like the two-sided conversation. Like, you guys can chat in the comments, help me out when things start flying off the board and exploding. It's pretty special, I think. Turned on the load. Didn't do load things. Try that again. What? Oh, okay. Sure. That makes sense. Yeah. No Corp said, I found your converter choice interesting. When I first heard you were going for diode rectified, I thought MP 1584, that or some... which probably can't remember the name of. It's much easier when you're not totally my very self. Yeah, I mean, that was one of those. I just went on TI's website and looked at what they had that was close to the bottom of their price range, and because I wasn't willing to spend much more money. All right, I think I need to shunt out the ferrite bead because of some combination of input and output capacitance. In this case, I want to try to fix it because having supplies that only kind of work makes me sad. And we're really only going to need a couple hundred milliamps out of these for our proto board. So, like, it's going to be fine. But as long as it's here, as long as we've got the caps, I'll use a couple of them. Yeah, there's a lot of good there's a lot of good power supply vendors out there. With regards, I think DI, that was Digital Integrations. And there's like MPS, which I think was bought by someone. Can't remember who. Or maybe they just changed their name. I don't know. I won't say it's difficult to keep tabs on what everyone's calling themselves these days, but it sure is annoying. There's a lot of acquisitions. But yeah, there's lots of good parts out there. One of the things that pushed me to this controller specifically is that I wanted gobs and gobs of margin on the maximum input voltage rating. Because, well, I was recently burned by that, so it hurt a lot, and I was like, alright, if there's one thing, I don't want this supply to fail for the same reason. I want it to fail for a new and different reason. So I might have went a little overkill on the, yeah. Alright. With the extra output capacitance, let's see how that ferrite bead's looking. Up to an amp. Hey, there we go, 5 amps out. 5 amps out, we're still regulating okay. It's better. It's not great. It's good enough. Good enough for me right now, today. So we're going to do the same thing, get this set to 2.5 amps. .5. There we go. And we're going to sweep the input voltage range. Oh, 16 might be a problem. I might need to make an exception for this one. No, we're still good. That is pretty darn good. Yeah, not quite 72. This one goes up to 40. Diodes, okay. Yeah, I was wondering if I moved next door to DigiKey if I could pick up there. Yeah. Shipping is a little expensive from DigiKey. That's why I kind of go back and forth, where if something's like $2 or $3 more on Amazon, it's like I like fast shipping for cheap. I'm not really all about the giant megacorps, but man, I like cheap fast shipping. So at 16 volts in, we're at 15.04 volts out. And when we crank it up to 30, we're at 20, 25, 26. We are at 15.01. Now that is what I call regulation. And we're sitting at, what are we sitting at for voltage ripple? We're at about 600 millivolts here too. It's not too bad. I'll calculate the percentage later. On the load regulation, we are sitting at 15.08 volts to, gotta get this dialed into 4.5. We're sitting at 14.8. What in the... Oh, we hit the thermal limit. See, but the great thing is that the supply doesn't blow up when you hit the thermal limit. It's one of the great things about these highly integrated controllers. They do a very good job of protecting themselves when you abuse them when you're doing line and load regulation testing. Yeah, alright. Looks like we don't have any new comments. Okay, let's calculate some percentages while that cools down a little bit. Now this one probably could use more thermal vias. The rate of power into the board. The board's not too warm, but the chip's quite warm. 30 volts minus 16, so we got a 14 volt swing. Then we've got 0.03 volts that changed with that 14 volt swing. Yes. 0.21% line regulation. That's a number I'm okay with. I don't mind that at all. Load regulation's a little bit less fun. We've got 0.28 volts of swing divided by 4.5 amps. It's in that 6%. Again, the difference between these two supplies and the 5 volt is insufficient output capacitance that's making it go into a weird mode of operation and puts more ripple and error on the output. Okay, time for efficiency. Yeah, 125, something like that. I think this part's 125. Okay, we're getting this thing set for an amp. Maybe? I'm hitting... Oh, there we go. There we go. 15. I'm going to take all the sig figs on this one. 15.5 watts out. 24 times 69. Oh, sorry. 0.7. We're at 92% efficiency. 1 amp load. How about 3 amps? Man, I'm loving having an electronic load, even if it's a pretty crusty one. This is a lot easier. Add this to the list of things I should have done a long time ago. We're at 91% efficiency at a 3 amp load. I'll let the board cool a little bit. Oh, that's not too bad. Yikes! Thermal shutdown's 170? That's hot. Oh, man. These controllers are not long for this world. I mean, better than the pile of fats, but yeah, that's hotter than I'd like. I'm going to need to make sure to stitch a lot of these. We've got like 6 or 8 thermal vias directly underneath the thermal pad. I'll need to add a lot more in the plane around, and we're going to have 4 layers probably. So we'll spread it out on the internal plane, on the bottom and top layers. It'll be good. You can kind of grow this upper area on the board to get the heat out. I also placed the diode right next to the controller, so I've got the mutual heating effects too. So by spreading out those components a little bit, not too much because we still want to keep the switch node small, but spreading those out more than, you know, 1/4 of an inch will definitely help the thermal situation as well. I did want to keep these small so they'd like fit on top of our old prototype. Okay, I think I've filibustered enough. I'm going to do the same thing here. I'm going to kind of preload the voltage measurement. We should be at about 14.8. Based on our load regulation test, we should be at about 14.8 volts, and we should be at 5 amps. We should be at 74 watts out. Dang, that's a lot of power for a board that big. Divided by 24 times. I just need to get ready with the current measurement. That was 5. Too much. Try again. Alright, we are at 3.47. So we're at 88% efficiency there. And just for kicks, that means that we were burning 8 watts in that tiny little board. Brilliant. That would be why it overheated so quickly. But hey, we're ready for phase 2. We're ready for phase 2 because I got all the measurements done. We were able to do line load, efficiency, all that good stuff. Which means that it's time to pile this back onto the inverter prototype. And we're going to power up the board with our new supplies. Now that we have some that don't kill themselves. I think we're done with the electronic load. Go ahead and unplug that. Put that off to the side. Cool. What do you guys think? I think that went pretty well. I'm pretty excited about that. To summarize that section of testing here, that block, and we were talking about 90% efficiency for conversions of pretty extreme voltage ratios. I mean, not super crazy, but I mean, it's enough that I'd think about it for more than 20 seconds. Maybe I'd think about it for 20 minutes. Joking. Yeah. I mean, I wish I could take more credit for how efficient that is. No corporation. I really wish I could, because I mean, a lot of the magic is in the is in the controller. A lot of the magic is in the sauce. Do I sound crazy yet? No, a lot of the magic is in that controller. It was just a good component selection for this application. Where it was like, we want dead simple. We want something that is just going to work. You know, I don't want to have to think about this. I just want it to work. Be good? Does that look pretty in focus? Hope it does. Yeah. Oh my goodness, yeah. I'm just happy that we can turn on the prototype and keep moving, right? We've got some fun circuits. We've got the battery charger, and I mean, that's got our fun CC/CV dithering where we tacked a bunch of analog stuff onto the feedback pin of a switcher. That's going to be super fun. Then we've got the 55 volt down to 24 volt buck that can hopefully spit out 5 amps. That's going to be super cool. But we were just kind of stuck because if we don't have like the housekeeping supplies, nothing else works. Okay. I think I need to take this test point out of here. Let's see if I can do this without burning myself. So I've got to get some wires in here. Right, looks good. I need to suck some solder out of there. Oh yeah. Yeah, and while I'm kind of not disappointed, but you know, I think it's a shame that we had to take this detour to fix these bucks. I think it's cool that today's stream is mostly testing instead of, you know, mostly building a board. Like, there's a lot of testing we've been delinquent on. Some of our previous streams were like 90% building a board and like 10% test. It's fun to switch that ratio a little bit. don't know about you guys, but I think watching someone solder is only interesting for so long. Hey, Dave. Oh, yeah. I can send you a link. So this is one where I'm sure that there are others. Like, I'm sure that you can find them from all the usual suspects, like AliExpress and so forth. But this one specifically, there was one of them, and you can probably find it if you search for electronic load on Amazon. There was only one that had Prime shipping, and that's the one that I got because I needed it in 2 days. So that's the one that I got. Are you noticing a trend with my decisions to buy stuff? It's usually can it get here immediately? If yes, buy it. What? I plan ahead. I swear. eBay? I was on Amazon, but you might find it on eBay. Hopefully I didn't misspeak. Googling? Or did... I don't know. Oh, right. There's a couple things we gotta take off this board first. Because we need to take our old circuit out of circuit. We need to take off our old ferrite bead. And we need to get this thing so that our old converters aren't fighting our new converters. Or, shorting them out, or whatever the case may be. Alright. I'm just going to hold on to these ferrite beads. I'm going to solder them back down, just backwards, so we don't lose them. Yep. Searching is the right word. 2 a.m. Holy cow. Holy cow. That's early or late, depending on whether it's... I was going to say whether it's Friday or Saturday, but that's silly. Because it's 2 a.m. That means it's Saturday. Welcome to Saturday. You made it. Oh my goodness. These thermal planes are huge. Come on now. This does not want to give. Alright, let's break out the hot air gun. There we go. Wow, that makes it fast and easy. Just needed a little bit of heat. Focus is real. The focus is real. Alright. Whew. Doing lots of things. Oh, come on now. Put it right back where it was. That was not the intent. There we go. Got the bead. Broke the circuit. Just tacking this part back down. There we go. She's on the board. Come on now. It's rotated the wrong way. It's sticking up. Just waiting to get caught by something and ripped off. Okay. Turn those. Now we've got to get the fuses pulled off. We got to sneak some wires in there and we will be good to go. Sorry about that. I'm a little bit out of frame. Yeah, this one claims an obscene voltage rating. I'll have to look at what it is. This one claims it can go up to like 300 volts and 50 amps or something. It was only a couple bucks too. I think it was like 25, 30 bucks. I'm sure that the FET would just go nuclear before it gets that high, but you know. Yeah, pulling off the PTC. Yeah, for how cheap this thing was. I still want to try our hand at making one that will be excellent. I think we can make a better one than this because, quite frankly, the whole manual came in Chinese and the voltage and current accuracy is not great, not terrible, about 1%. It's just got... it just doesn't look that great. Doesn't feel that great. The whole thing came kind of warped. I think this is one of those, it's a good stopgap. It's better than buying a bunch of power resistors, but I wouldn't recommend it. Better than nothing. Yes. Okay, yes, I would say yeah. Yeah, plus not programmable. Good point. And I am definitely concerned about how slow the control loop is. Okay. Got a couple more of these test clips to pull out. Because our test clips now appear... oh goodness, this board is hot. This board is very, very hot. And so are all the caps, and so is everything. $12 volt. Let's get this one out. Sorry about the terrible framing. Everything's blurry, but I'm just trying to not burn myself right now. Okay, there we go. So we just pulled out the test clips for the 12, 5, and 15. Going to wire them all into 12 volts, or the 24 volt input, and feed them all into our test hooks. So we've isolated the supplies. This will work great. Okay, let's get the inputs wired in first. Five, 12, 15. I don't know if these are all gonna fit in that one test point. I can probably fit two. I don't know about all three. It's a lot of wire to cram into one little test point. Alright, there's two. Yeah, there's no way I'm fitting 3 in there. I'll use this other nearby test point. Alright, so that means I'm going to be in similar pain with ground. That means I've got to find myself another ground test point. That's a shame. Alright. Yeah. I'm pretty excited about the prospect of building electronic load. I've got a couple fun projects. Like one that's been on my mind for a pretty long while is a thermal monitor for the 3D printer. Basically something that's controlling mains. Like it's already got a fault handling like loop where if it notices thermal runaway, it will cut power to the heater and stuff. But that doesn't account for more subtle failures. What in the world? What am I hung up on? Doesn't account for more subtle failures, like if the FET controlling the heater fails short. And I really, really don't want to burn down my house. So I think some kind of TCO type functionality would be pretty good. So just building a little board to accommodate that seems like a good use of our time. The motor controller still on my mind. Electronic load still on my mind. Maybe I should think less. But there's going to be big, exciting, fun projects coming. Yeah, and I think, you know, while it's definitely applicable to 3D printing and 3D printers, right? If you guys watch the news at all, you know, there's been a couple pretty notable fires from that. But there's lots of other things that people do, right? Like smoking meats, where you have a heating element on for a long time. And even if you trust your controller and you've got a pretty fancy one, adding an extra layer of protection is always good. Adding a little bit of fault tolerance is always good when you have so much at stake. Like, what? Oh. Mm-hmm. Printer. The noise? Is the noise the 3D printer? Yeah. Oh, when we were just kicking off the stream, I was chatting a little bit about the noise. Yeah. What we're printing is the new version. Oh, come on. This is, remember that time where I said this iron doesn't seem to spit out a lot of heat? The power output is set to like 10% right now. Why? It's not melting the solder. The temperature is not up to snuff. And it's just super not working. So I've got to bump the temperature, which is literally like the whole point of getting the direct heat iron. Not needing to bump the temperature. Just frustrated. It's sitting there like, oh yeah, I'm 55 degrees. Clearly you are. All right. Alright. Trying to get this actually into the hole rather than near. There we go. Perfect. It's in. It's not pretty, but it's in. Wow, that was painful. Line voltage is 120. It's 120. Okay. Why? What's the line voltage where you are? Probably 240. I think it's 240 most places. It's kind of a cheating guess. That is the 12 volt supply. Wow, super glad I didn't just solder that into 15. Yeah. With regards to the noise, hopefully it's not too bad. That's why I'm switching the mic. I listened to what you guys would hear if I wasn't using a mic literally strapped to my face, because I can get rid of the noise a little bit better that way, get better separation. It was a little bit too much. Come on now. There we go. Now we have 15, 12. We're getting there. Point-to-point wiring. I'm remembering why I do this less. It takes a lot of time to wire something up point-to-point. When you've got a printed circuit board, and you can just fly through assembly and all these things. Not so when you're working with point-to-point wires. Looks like there's been some traffic. Arcade-like sounds, yeah. Line voltage, understand the noise now. Mains. Sometime the line voltage mess with soldering. Yeah, this has got an AC to DC supply in there. Which, I mean, maybe it's messing up, but it doesn't drive the heater with mains for this specific iron. So I think I'm in the green there. Gotta get a little creative with how these solder in. Yeah. 120. Some of the. Really? Are you in Australia? JD, I feel like you've got to be in Australia, because Australia is notorious for having terrible power integrity. So what my understanding is that there's some places in Australia that have earth return. Like, they literally use the ground as, like, neutral. Wow, man. My voice is all over the place today. I must have been, like, screaming all day yesterday. Not literally, but the equivalent. Yeah. So, that would add a little bit of impedance, using earth as your neutral conductor. Yeah, that's not great. Speaking of not great, this. I'm gonna see if I can get the third supply wired in. There's a little bit. No, not a chance. Okay. That looks disgusting. Let's keep it. This is my ugly baby. Thanks. I was blanking on the proper word for it. Single wire earth return, otherwise known as a bad time. Holy cow. There we go. There we go. Well, it's not my best work. But it just might work. I just need a good ground location for this third power supply. Where is ground within reach? Bat minus, I'm pretty sure that's ground. Let me just double check that's actually ground. Really? Pennsylvania. Pennsylvania. I didn't realize they had issues with power integrity over there. Alright, yep, that's a nice solid ground location, so I'm gonna pull this wire kind of back and under and around and down, and we'll get that wired in. So now in theory, we've got 5 volts, we've got 12 volts, and we've got 24. Oh my goodness. Does the prototype work again? I don't know, but I'm hopeful. One small detour, and I think we might be there. I don't know, it seems pretty safe. Like, if the earth that you're standing on is at a potential that isn't 0 volts with respect to the power company, it's still 0 volts with respect to you. So I don't think you'd really get zapped. RCDs. Okay. Do a quick check of power ground shorts. 24 to ground. Good. 15 to ground. Good. 12 to ground. Good. 5 to ground. Good. What? There we go. Didn't have a good contact on there. Okay. Should be ready to fire it up. Oh, GFCIs. Yep. Yep. Oh, sorry about that. I was touching my face and I bumped the microphone. I'm sure that was pleasant. Okay. Okay, so now we're basically doing the same thing, only different. So now what we're going to do is we're going to be doing line and load regulation testing for the flyback. Finally get to test the flyback. Remember that? That was like, what, 2 weeks ago? 3 weeks ago? Oh, look at all those pretty LEDs. I'm a sucker. Now we've got 2 redundant LEDs on every power supply. And now for something completely different. Yeah, I like that. 5 volts, 15, and 12. Sweet. If I have a spare moment, I might assemble the fan monitor. We've been really cruising this morning, but I don't know. I don't know if we'll have quite enough time. We'll see how long this takes. Oh, right. Forgot. We have to jumper 24 volts over for this guy. That became a little easier. Got all these great test points for that now. Alright. 24. There we go. So one of the things, I don't remember if I was able to show you guys this. There's a little bit of a problem with this rail. I don't know if you can hear that. There's a little bit of like this audible coil whine. And oh, I want to tack a little wire on here so I can show you better. Show you better what I want to describe. What? Okay. So I want to show you this net here. Dope. My goodness. Found cheap synchronous supplies. Yeah, so there are cheap synchronous supplies. I found cheap synchronous supplies. The problem that I had with them is that the cheap synchronous supplies did not describe their implementation of the low side gate drive very well, or how they were preventing or guaranteeing a 0 dead time or a lack of shoot through. And we do have 5 amp outputs. Good grounding, substations. Cool stuff. Yeah. So I don't know. I'm sure there are other options that could work, but there's just nothing that really got me excited where I was like, yes, I can design this quickly without issue. Okay. So, now remember, this is an isolated supply, completely isolated from the primary. And I need to get this out of AC coupling mode. We want DC coupling for both of these. And we're going to want to crank this up to 5 volts per division. DC. Alright. So, what do we have here? Menu, trigger, channel 1. Really? There we go. Oh. Sorry. I will show you. I'll pull it over. I'll show you what I was doing. Here's what I was doing. Sorry, JD. That's what I was doing. I was tacking a wire onto the float net. So this is on the flyback. There's the intermediate voltage regulating net right after the transformer through the fuse, where I've got a couple shunts, and that's what I was showing. So what you see here is my problem. See that ripple? The current gain is a little bit too high, and I'm playing right now in a LT Spice. I'm playing around with a couple sims on methods of reducing that oscillation, because right now it's audible. It's audible because we're tugging hard enough on the feedback to cause it to turn off the gate drive completely, which is more than we really need to tug on it. Like, it's fine. Like, these LDOs are rated for up to 35 volts, and we've got clamps at 20. So if we start pulling a couple milliamps through the clamps, it'll keep our voltage under control. It's just really, really light load where we have serious problems with this. And when you're at really, really light load, if your efficiency's terrible, it doesn't really matter because you're not talking about very many watts. Like right now, with our supply, right? We've got all these LEDs on. We're pulling 0.03 amps. I'd want to use this meter. I'd want to use my good meter to measure the current into the board. And in fact, no, I can't. We're going through other things. But if I was going to measure it, I'd want to measure it there. Searching through here, because there's one resistor. There's a V feedback, R122. And if we replace R122 with a 64K resistor, that should, or anything greater than 5.11 should be acceptable. But I was playing with a 6.49 because it already exists in our design. So if this value works, I'd prefer it. Basically what it's doing is it's limiting the impact of the feedback to not pull us down to 0% duty cycle, but to pull us down to, like, you know, maybe 10%. R122. There it is. 122. I want to keep this resistor around. I'm gonna tack it onto our optocoupler. Oh no, I've got a stray resistor right next to the one that I need. One moment while I verify. 6.49. Yeah, that's a 5.11 that was right next to it. Weird. Maybe it got put in the wrong bin. The soldering skills? You mean the I'm trying to is that a subtle dig or is that serious? I mean, I hand soldered all the 0402s, which is pretty cool. Or no, these are 0603s. But are you just saying like the mad? I mean, it's crazy, right? This thing's insane. It's got 3 protoboards hanging off of a larger protoboard. Anyways, let's turn the thing on. Hey, look at that. So our quiescent current's only a little bit higher. It's actually about the same. But by reducing the impact of that feedback net, I think we can get by without an optocoupler. Or sorry, without an integrator on the... Alright, got this in volts mode here. And now I want to look at the float voltage. What? Oh. Isolated. I was charging a capacitor. Yes, we're up at 20, so we are clamping. We are clamping a little bit of voltage through these guys right here, but they're not too warm. So we're not passing too much current through them, which is obvious because we have less than 2 watts coming into the board. Now, oh, and here I thought I was done with the electronic load. That's what I get. I'm gonna need a couple more alligator clips. So now we're gonna need to be pretty careful with the electronic load. We don't have a whole lot of... Don't really need a lot of amps. But I'm going to see if I can get this thing tuned up on like the 5-volt rail. We just want to pull like a 1/4 amp. I don't even know if this thing can be set that low. Got 0.3, 0.2, 0.1. Yes. Okay, great. We can set it to 0.1. Okay. So now what I'm going to do is I'm going to load this float rail. Hey. What in the world is up? Now, so the input power to the board is now... Yeah, we're able to support 0.1 amps out on the flyback. Okay, I want to get a DMM set up so you can see that better. There it is. Okay. Okay. And I want to get this set up so you can see the voltage as well. I think we've done it. I think we're ready for the testing. Hopefully I'm not skipping half the words. I'm getting excited. I can skip words when I get excited. Let me know if I need to circle back and explain something. Okay. Voltage monitor. Got a voltage monitor, and we have a current monitor. Okay. This is a little sketchy, but I think it'll work. Okay. Let's just make sure. Yep, so we're getting 0.1 amp out, 19, so we're getting, what, 2 watts out? We can tweak the current a little. Oh, look at her go! We should be able to get up to about... Yeah. Whoa! So we're able to get about 5 watts out of this supply. That's awesome. Okay. I'm going to turn it off. And I'm going to come down to 5V0. Okay. And we're going to turn it on. Sorry, that's... What? Ooh, what? I'm getting 15 volts on the 5 volt rail. That's not a good sign. Why am I getting 15 volts on the 5 volt rail? Why am I getting 5 volts on the 15 volt rail? Ah, I clearly installed the wrong part in the wrong place. My bad. Well, they're just LDOs, so it doesn't really matter, but I should probably flip that around. So if we come on the 15 volt rail, okay, I think I gotta read comments. Look at the soldering skills got, is isolation broke? Nope, this is an isolated AC to DC supply. Yep, yeah, they're powered by, yep, you're right. So, yeah, right now, the DC input through our lab power supply is isolated. These are obviously isolated because they're battery powered. And then this is isolated in that AC to DC converter. So, yeah, we're floating, but we're coupled pretty tightly to ground because we're capacitively coupled to the ESD mat. Well, we're a couple megs. We're a couple mega ohms away from ground. What you can see on the scope, that's the yellow, channel 1 is ripple on that intermediate rail, and then the blue is ripple on the LDO output. And so we're on the 15 volt rail. Oh, I'm on the wrong LDO. Okay, so now we're on the 5 volt rail. Measuring 5.3 volts on that LDO. That is a lot. Wonder why. That's weird. Let's give it a little bit of load. Whew. Something seems wrong. Something seems very wrong. Something seems very, very wrong. This LDO seems very unhappy. Yeah. Which is weird because these are rated for 35 volts. So we should be fine. But this is dropping out of regulation when we pull almost no current out of it. Let's try the adjacent guy. Let's try our adjacent supply. So we're at 15. Whoa. 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 Alright. Something's hot and kind of screeching. That's usually a good sign. Audible noise, usually a good sign. Alright. Oh. Sorry, the scope was grounding us. Hard to earth ground. Okay. Okay. Huh. That was weird. So now definitely hearing an audible, like, coil whine. So that's interesting. Super unsure right now. That describes how I'm feeling. Yeah, it's like a really high-pitched whine. Okay. I hate how close together these clips are. Okay. So we got a 20-volt output. Maybe it's just our electronic load is like putting a step. Maybe it's like being really aggressive because the control loop's terrible. I'm going to grab a couple high value or relatively high value resistors, like 150 ohm. And we'll just add a couple of these guys in parallel and see what happens. Because I did load testing on this before and it worked. Actually, I think I'll keep picture in picture. Yes, this is really confusing and concerning. That would be how I describe this. Confusing and concerning. And we were operating at 18 volts in before, now we're at 20. Should it be that different? No. Why is it different? No idea. Well, I did leave it sit for like a day, so yeah. Okay, so I'm just gonna take this and clip it to like 4 of these resistors, and then I can choose how many I want in parallel. Okay, we're gonna try the 15 volt rail. Oh my goodness, wait a minute. Wait a minute. Something's super wrong. Because these supplies are installed correctly. And the 7805 is actually giving us 15 volts. Have you guys ever seen this before? Here, I'll bring the mic real close. Can you guys hear that? High pitch whine? Here, I'll unload it. It says unloaded, more loaded, more loaded. That's the noise. I've got the high pass filter on, so I don't know if you guys will hear it. But yeah. So we're sitting at an RMS voltage of 20 volts. And, oh, wait a minute. Channel 1. We're getting 5 volts out. 5 volts DC. Wait a minute. This is working. This is working. Let me get the multimeter pulled off the float rail. Let's measure this rail instead. See, look at that. See, we're at 4.9. I have no idea what I was smoking before. But there it is. So now we're getting 5 volts out. And uh, 5 volts out. Whoa. Oh, right. Sorry. Yeah, I'm not probing the source. So I should be able to get 250 milliamps out of either of these. Whew. Our Zener clamp is getting a little toasty. Our Zener clamp resistors, these 1 ohm resistors, they're whew, as I load this thing, they're getting pretty feisty. Okay, let's unload them. Yeah, so cranking away at the max duty cycle for a while. Super not good. Alright, let's do a quick. Let's get this thing cranked up to 250 milliamps. I want to see this thing at 250 milliamps. Switching over to the electronic load again. Let's see if this thing can do the business. Being pretty careful. I don't want to load this thing with, like, you know, an amp. Alright, that's going to be way too much. Okay. One moment. Oh. And this is stressful. Okay, so we've got our load set for 1.2 amps. Alright, 1.2 amps. Let's see what happens. 5 volts, 1.2 amps. Alright, so I want to measure the efficiency of this. So we got 5 volts, 0.13 amps, which is 50% load. So we're getting 0.65 watts out, and we are going from 24 times 0.35 minus 0.3 24 times 0.07. Whew, we are a smoking 11% efficient. Yeah! Which isn't terribly surprising, right? We've got a 20 volt bus that we're regulating down to 5, so at best we're going to be 25% efficient. Hey man, how's it going? Try harder? Yeah. 11% efficient. Mmm. Tasty. But it's maintaining regulation. In the spirit of that, oh boy, oh, banana clips are going nuts. Let's switch over to the 15 volt rail. Let's see what we can see. So now the output power is going to be considerably higher. We are going to be at the same current level, so we'll be at 1.2 watts out. And just need to know how much power we're taking in. Oh my goodness. Same deal. Times 0.33. I must have had something hosed up with my probes before on the grounding, because it was behaving really weird. Yeah. Tasty 11%. Alright, so on the 15 volt rail, we're 30% efficient. 30% efficient. That's much better for the LDO. What I notice is that it looks like we got a little bit of headroom here. Like, I'm turning up the output power, but the input power isn't changing considerably. So it seems like basically pulling any power off this rail is causing our switcher to go into maximum duty cycle mode. And when it does that, we pull about... Yeah, this isn't so bad. I want to try to see what that blip is. I'm hearing something. It sounds cyclical, but I can't... I don't see anything in the output waveform. It might actually be my transformer like vibrating against itself. Oh my goodness, it is. Because when I touch the transformer, I think my wires are vibrating against each other. That's not good. That's something to keep in mind moving forward. And I might need to revisit these Zener clamps. But anyways, we're getting... So our gate drive supply can pull plenty of current. That's what this one's for. Looks like we can get up to... Whoa! Yeah, about 300 milliamps before the thing just dies. So you can get about 300 milliamps. That's not so bad. Yeah, I might have to epoxy the transformer. The transformer's getting a little warm. It's nothing too bad. It's a little warm. I might need to get a thermal camera. Take a look at that. I don't have one. Whoa. What is going on? When I touch this cap, the noise is reduced. What in the world? What is this? What is happening? Is this thing generating high enough voltages to like arc over or something? And I'm providing a capacitive coupling path? Or is this actually like not soldered down to the board and I'm pushing down on this capacitor? Okay, I want to see if you guys can hear this. Okay. So you see the weird glitches on the scope. You hear this noise. I push down on that cap. It all stops. What? What? What is that? What am I supposed to do with that? Here's what I'm going to do with that. I'm going to add a 4.7 microfarad 50 volt rated cap. Or 35 volt rated cap. Because it can handle the 20 volts. I'm going to put it on the output and see if that helps. This could be another instance where the ESR of that output cap is causing us some issues. Maybe adding a little bit more low impedance output capacitance will help. Not a clue. More solder? Yeah. Well, yeah, if our output capacitor is occasionally removing itself from the circuit, oh my goodness, that'll have an impact. I might just reflow it. Might just get it warm and make sure. It seemed to be okay, but... Whoa! Yeah, definitely that cap was not in circuit, because I came in here with the soldering iron. I don't know if you guys could see that, but the diode flashed for a second when I came in here and soldered the circuit, i.e. I was completing the circuit with the soldering iron tip and had charged the capacitor. Oh, so maybe it'll work a little better now, eh? Maybe just a little bit? Hey, look at that! We've got an output cap. So that's good. Woo! I hope that's warm from the soldering and not from the ripple current. I don't know. Oh yeah. We're getting the power out of this guy now. 0.33 amps. 0.38. Power OK has failed. So looks like I'm using the electronic load to find the maximum power point. I'm getting 4.5 watts, 5.3 watts at a maximum. So the combination of both of our rails can pull 0.37 amps. That's a little bit less than designed, I think. I'll have to make sure that's enough. 400 milliamps for gate drive. Man, I've got to think that would be enough. Oh, yeah. Oh, I'm sure it does, yeah. So right now, we're going with... we're getting 5.3 watts out of the supply. Let me calculate efficiency here, because it's not directly answering your question, but it's indirectly answering your question, right? If the efficiency went up and the power output is about the same, that would mean that we're dissipating less heat overall. Okay. Insert, we want 14.9 times 0.36. I like it when my power supplies don't make noise. So we are 45% efficient. Unfortunately, I smell something. The resistors are warm. Nothing crazy. Woo, those diodes are a little warm. It's alright. So we're 45% efficient right now. And the output ripple looks excellent. The cap is getting a little warm. I'll probably want at least 2 of these in parallel or add more MLCCs. There's a little bit too much ripple current going into that electrolytic. LDO's not excessively warm. This is pretty solid. I'm a fan. Yeah, it kind of smells like hot electronics. Yeah. Yeah. This is awesome. I love this little converter. All we had to do was tweak that resistor to get rid of the oscillation at light load, and boom! So yeah, that is something I'll need to remember, because we're driving some gates, and I honestly don't know if that is enough, because like we're driving the full H inverter with this, we're driving the push-pull stage of the PFC with this, there's a lot of instances of this circuit that need to be considered. And I really don't know if that's going to be enough. If not, what I'll probably do is replace this with a full H or a push-pull. Just a different topology of basically the same thing, where it's the little transformer getting power across the isolation boundary. The flyback's just a little, I don't know, it's good, but that's a lot of parts. That's a lot of parts for one of these supplies. That's the real thing that's turning me off, right? We've got all the Zener clamps, we've got all this nonsense. There might be a simpler way. There might be an easier way. Yes, we got 0.36 amps max. But that's cool. It's so cool that we have isolation established, getting power across, you're getting 5 and 15 generated on the low voltage side. Or sorry, on the high voltage side. Don't do me like that, multimeter. So now we got the 5 volt, 0.35. Yeah, I like it. I like it a lot. So now the reason why I'm doing this is because this LDO is dissipating a lot more power. That was hot. Oh my goodness. That was hot. Oh my goodness. Yeah, because we're dropping about 15 volts. When you're dropping 15 volts on an LDO, it's gonna have a bad time. With the heating, I can't remember for an electrolytic. It's not uncomfortably hot. It's a little warm. For an MLCC, it would change a lot with temperature. For an electrolytic, because electrolytics don't have the same voltage bias effect as MLCCs. So we can get about, yeah, 0.25 is probably the absolute maximum for the 5 volt rail. That's what I calculated it to be. I don't know if I'm comfortable with it getting that hot. I might call it at 0.2. Like when I did 0.25, this thing was getting up to TJ max, right? I don't really want to push it that hard. So you can get 0.2 amps on the 5 volt. Uh, 5 volt, and then this one was on the 15 volt. Cool. I don't know about you guys, but I'm satisfied. This feels like success. This feels good. Was that a joke about success? 15 volts, 300 milliamps? Yeah? Yeah, I don't know. I don't mind. Seems good to me. One thing I'll do is just for funsies, I want to capture the turn-on transient of this supply. Just make sure that we're soft starting in a reasonable way. Yep. So we're triggering on. Let's trigger on channel 2, rising edge. Let's turn it off. Wait for the output voltage to drop. Turn on. Okay, maybe I zoomed out a little bit too much. it would appear I have zoomed out a little bit too much. Oh, look at that. Look at that beautiful soft start. And if we unload it, let's do the same thing. Beauty. Comes up a little faster, obviously, because we're basically in a constant power. We're regulating duty cycle, so yeah, you can't ask for a much better turn on transient than that. That's nice and gentle. And that's exciting. I don't know if I can do the fan monitor today. I'm feeling pretty wiped, but it was a lot of fun. Oh my goodness, this was a lot of fun. Yep, unloaded is in no low. Sorry. Unloaded is in. Yeah, so we're coming up faster because we're pulling less power out, so it's charging the output capacitors faster. Oh my goodness. There was a little bit of a battle with the output capacitance on these, but I don't think that was so bad. I think that was alright. Then we got them tacked onto the old proto board. These are kind of in the way, which is unfortunate, but we don't have too much assembly to do underneath or around. We can kind of push them out of the way when we're working over there. The UPS prototype lives on. Yeah, this is awesome. A couple things before we go. This is closing soon. The sticker giveaway is closing soon. For a couple people that haven't done it, there's some people worried about how much it would cost to ship a sticker overseas. It's not too bad. It's like cheap enough that I'll say it's free. It's like $1. It's no big deal. So yeah, seriously, if you guys want one of these, just throw your name in the hat. Not many people have signed up, so your odds of winning are really, really good right now. So be super cool. Okay, interested in seeing how we can figure out how to do the ripple current stuff properly. Gotcha. Good point, No Corp. So how I like to do that is just in Spice, like in a simulator tool. What I'll do is I was just making sure it wasn't getting hot. What I'll do in the simulator is I will add the ESR and the ESL as discrete components in a Spice sim, and I will compare the ripple current between the different components. So that's how I'm going to optimize this. I'll pull in the ESR and ESL for some MLCCs. I'll pull in the ESR and ESL for some output caps, and then I'll make sure that we're not overstressing anything and the current's dividing nicely. So that's one way that you can be a little more subtle than just throw all the caps on, or there's analytical ways to do it that aren't too bad. Oh, no problem, JD. This was pretty sweet. And like, it's moments like this where I get excited, right? Because we've got all this downstream circuitry, right? We've got like the RGB fan controller, we've got the fan monitor, we've got all this sweet, fun stuff. And then it's like, oh, and by the way, the hot swap controller still works, so we can just like unplug the supply and it's just fine. It's just so cool. It's just fun, right? Because now we know that we can operate this board up to 30 volts on the DC input. This is going to be a fun project. I bet that by the time we're done with this proto, we can get to a first rev of the proper UPS mainboard that works pretty well. If we find the kinks here, it should just be rinse and repeat, and we get what we need down the road. Yeah, there's a lot of fun times to come. There's gonna be a lot of good. Cool. But yeah, so get your sticker if you want it. yeah, just want to thank you guys for watching. Hope you learned something today. Hope you enjoyed. We'll see you again soon. Got videos coming out on some of the streams and whatnot over the next couple weeks. Should be a lot of fun. Next week, I think we're doing the 24 volt backup, so that's the 50 volt maximum down to 24 volts, so it's a third power supply, so we can feed it from either DC input or tap off of the battery directly. If I'm feeling lucky, maybe we'll do the battery charger as well, which ends up being a constant current, constant voltage supply. So definitely tune in next week. You won't want to miss that. It'll be next Saturday, same time, same place. Well, as always, see you in the next one. Bye.